Alright, in this section, or this chapter, we deal with derivatives. And we're going to look at only 3 sections in chapter 11. Derivatives of logarithm functions, derivative of exponential functions, and applications in business and economics. So in 11.1 we deal with logarithms. So here's the basics of a logarithm. The logarithmic function y equals log base a of x is the same as a to the y equals x. So notice the logarithm equals y, and over here the y is in the exponent. So that's basically what a logarithm is. The logarithm is the exponent. And a lot of times when you're dealing with a question dealing with logarithms, they're trying to figure out what the exponent is. The most common base for a logarithm is base e. Logs with base e are called natural logs because they deal with the natural world, physical sciences. But you can write log base e of x, or you can write just ln of x. Right? And this is the graph of ln of x. The second most common base for a logarithm is base 10. Logs with base 10 are called common logs, or just logs. So log base 10 of x can be written log x. You don't have to write the 10. There are 9 basic rules we use to work with logs. They're on the next page. One set of 9 rules is for any base, and then another set of 9 rules is for base e. Alright, so like I said, there's 9 rules for logarithms. First one is the definition of logs. It's the most important rule of all, and you'll use it about 90% of the time to solve problems. The second one says log of multiplication equals addition of the logs. This one, log of division equals subtraction of the logs. Something raised to a power, you can bring the exponent out front. And if it's the base raised to that power, you bring the n out front, and then just log base a of a is just 1. So 1 times n is n. Log base a of 1 over x equals negative log base a of x. Log base a of a is just 1. Log base a of 1 is 0. A raised to the log base a of x is just x. And your change of base, log base b of x equals log base a of x over log base a of b. The same thing's true for natural log. So in 11.1 they talk about a table of life expectancy of people born in certain years. Projections all the way to the year 2050. These data can be modeled by the function 8.7744 plus 14.907 times the natural log of x. And so if we want to find the rate of change of this function, we have to take the derivative, but we have a logarithm, so that requires the derivative rule for logarithms. Right? The graph of the natural log of x is always increasing, so the slope of the tangent to any point is always positive. This means that the derivative of y equals ln of x is always positive. So if y equals ln of x, then y prime is just 1 over x. You just take what's in here and write 1 over it. So y equals x cubed plus 3 ln of x, find y prime. So the derivative of x cubed is 3x squared. Derivative of this is just 3 times the derivative of ln of x, which you know is 1 over x. And then we simplify it that way. This one we're going to have to use the product rule. So you got the first guy untouched times derivative of the second, 1 over x, plus the second untouched times derivative of the first. When you multiply it out, you get this guy here. So notice if you take the natural log of a function, not just a variable x, but a function, you write 1 over u, like you would expect, but you have to follow with the derivative of the interior function. On this one, they give you a natural log of this, and they ask you to find the derivative. Well, it's just 1 over it times the derivative of it, and you clean it up there. 1/3 stays out front. This is 1 over this times the derivative of that, and you multiply it out. Notice I cancel a 3 here with a 3 there, leaving me with just the 4 and the 1. On this one, we're going to use the quotient rule, so you get the bottom times derivative of the top times 2. minus the top times the root of the bottom over the bottom squared. Now you can cancel your 2x plus 1's. You're left with just 2 and this guy here all over that guy squared. Now we can use some of the rules of logarithms to rewrite functions so that finding the derivative is easier. Some of them are log of multiplication equals addition of logs, log of division equals subtraction of logs. Something in the exponent can be brought out front. Those are basic rules that we can use to help us simplify a fraction or simplify an expression before we take its derivative. Alright, so this guy, if you write it separately, you can write this as ln of x plus ln of this guy. And you can bring the 10 out front. That's about as simple as you can make it. Now when you take the derivative, you just get 1 over x. You get your 10, you get your 1 over that guy times the derivative of that guy. And now you just multiply it out and simplify. This one, the 4 comes out front. And now the division here becomes subtraction. And the cube root becomes, or is 1/3 power, so it can come out front. And the denominator you can't do anything with. Now if you multiply the 4 times each one of these, this is what you get. So now when you go to take the derivative, you leave the constant out front. You take 1 over it times its derivative, minus 4 times 1 over it times its derivative. And when you clean it up, it looks like that. Number 4, lifespan. That was what we were looking at in the very first question. So you want to take the derivative of this. So derivative of constant is 0. Derivative of this is just the constant times the derivative of ln of x, which is 1 over x. So this is your derivative. Set it equal to 0, and it has no critical values, hence no maximum value. And thus that means there's no maximum lifespan in this function. And what if you take the limit as x goes out to infinity of the derivative? Well, you're taking the limit of this guy, and when x goes out to infinity, that approaches 0. So your limit is 0. So what do the results tell us about the average lifespan? It tells us the lifespan will continue to increase, but at an ever slower rate. So here's our cost function. And they ask us to find marginal cost when 100 units are produced and explain its meaning. So you have to take the derivative. Derivative of that guy is just 0. This guy is out front. 1 over it times the derivative of it. And you multiply it out and you get this guy. So now when you plug in 100, you get 6. So that means when 100 units are produced, the marginal cost is $6. Also, you can say the approximate cost of producing the next skateboard, or the 101st skateboard, is approximately $6. Sometimes you'll have to use your change of base formula. So if you got a base that you don't really know or you don't want to work with, you can introduce a new base, which is in this case e, and the x comes up front and the base here comes below. Alright, if y equals this, find y prime. So let's rewrite it using change of base formula. So you got ln of the top divided by ln of 4. And you can bring the ln of 4 out front and write it as 1 over ln of 4 times that guy. So now when you take the derivative, remember this guy is just a constant, so you're really only taking the derivative of that guy, which is 1 over it times the derivative of it. Which gives you this guy. Note, changing the base from 4 to e makes it simpler. Any other base than e would have the factor 1 over ln of that as a factor. Alright, example 7. We've got the original function and we take the derivative. We're going to use the product rule here. First, derivative of the second plus second, derivative of the first, and then the derivative of x is just 1. So you get this here, and 1 and minus 1 go away, so you just get ln of x. So here's your original function, and here's your derivative, which is just 1 of ln of x. And b says, what are the critical values for this guy? Well, it's at x equals 1, And C says, does it have relative max or min at x equals a? Yes, it does, at 1, -1. So now let's do some similar exercises. If you got f equals this guy, your derivative is just 4 times the derivative of ln of x, which is 1 over x, and you get 4 over x. This guy's derivative is 1 over 8x times derivative of 8x, which is 8, and the 8's cancel. This is 1 over x to the 4th times the derivative of x to the 4th, which is 4x cubed, and 3 of the x's cancel, and you're left with 4 over x. This guy is 1 over 4x plus 9 times the derivative of 4x plus 9, which is just 4. And so you get that guy there. This guy is 1 over the 2x squared minus x times the derivative of that, plus the derivative of 3x, which is just 3. 13, find the derivative, and then show that part B is the same as part A. So you take the derivative of this and you get 1 over x. Here you get 1 over x times 1, which gives you this guy here. And part B, if you rewrite this using 1 log, you can write it this way, and that is exactly, this is what we had in part A, and this is what we have in part B, so I've shown that they are the same. And this one, when you take derivative, you're taking, I rewrote it using the log rule, so I wrote natural log of division equals subtraction of the logs. And now when I take derivative of this, it's just 1 over that times its derivative, minus 1 over q times its derivative, and you get this guy here. Same idea here, do a rewrite. You can bring the 3 out front, and multiplication here becomes addition, and the 1/2 power comes out front. Now when you take the derivative of this, just 3 times 1 over x, plus 1/2, 1 over x, plus 1 times the derivative of x plus 1, which is just 1. And there's your answer there. 27. You're going to use the quotient rule, so you get the bottom times derivative of the top minus top derivative of the bottom over the bottom squared, which gives you this guy here. And then this one, you can bring the 2 out front before you take the derivative. Now when you take the derivative, you get 2. You get 1 over x to the 4th plus 3 times the derivative of x to the 4th plus 3. And you get this guy here. This one, you bring the 4 out front and take natural log to the 3rd times the derivative of natural log of x, which is 1 over x. And so when you multiply that out, you get this guy. Notice this isn't ln of x to the 4th. It's ln of x times ln of x times ln of x times ln of x. It's ln of x quantity raised to the 4th, not ln of x to the 4th. Alright, this one they give you the cost function, asks you to find the marginal cost, so you take the derivative. Then they ask you to figure out what the marginal cost is when x equals 200. So you plug in 200 and it's approximately 1. So the approximate cost of the 201st unit is $1. And what do they say about the function total cost? It's always increasing, so the slope of the cost function or marginal cost is always positive. And I drew a picture of it to show you. Here's the original function c, and here's the point where it touches as the tangent line at the point 200, and that's your amount of money that you that's your cost function when you produce 200 items. 45, you got the revenue function, find marginal revenue and plug in 100. So you take the first derivative, and then here to clean up the complex part of the fraction, you don't want a fraction within a fraction, so you got to multiply by this common denominator, top and bottom. And when you do, it cleans up this way, and then you can factor a 10 out of that one, and you can pull a 10 out of the second one as well, and then it cancels, and then you get this guy here. Now when you plug 100 into that, wherever you see an x, you get this here, and that equals $309.67. So at 100 units sold, selling an additional unit, the 101st, is going to yield you $109.67. So this one gives you the supply of a product at price P. Find the rate of change of supply price, so you take the derivative, you get this guy, and they ask you to find the rate of change when the number of units is 33, so you plug in 33 and you get $1.50. Then if you take the actual price change, it's $1.48, which is very close to our actual answer.